This video is about solving a system of linear equations with three variables and three equations. In previous videos, we dealt with two variables and two equations, and we saw that we could solve using the substitution method, the elimination method, and solve with graphing. Now we're going to go to three variables and three equations. If we have three variables, that means we're in three dimensions. So it's going to be very hard to do via graphing because it's kind of hard to graph planes in three dimensions. And so we're going to only focus on the algebraic approach to solving system of equations in three variables and three equations. If at any point you want to look at the previous solving systems of equations, those will be linked below. If we're trying to solve a system of equations with three variables and three equations, what we're going to do is pick two pairs of equations. With those two pairs of equations, we will eliminate the same variable in each pair. We can do that by using the elimination or substitution method we have seen earlier. Once you've eliminated the same variable in each pair of equations, then you'll be left with two equations and two variables. With those two equations and two variables, we can solve those using the previous methods that we've looked at. Once you solve the two variable, two equation system, there will be one variable remaining. It will be the variable you eliminated. And so we can plug in our numbers and find that last variable. So we pick two pairs of equations, eliminate the same variable in each. Then we'll be left with two equations, two variables, solve those, plug that answer in to find the last variable. Let's look at an example. Here we have a system of three equations and three variables. Our variables obviously are x, y, and z. The first equation is x minus 2y plus z equals 6. The second equation is x plus 4y minus z equals 10. And the third equation is 2x minus 6y plus 2z equals 6. My first step is picking pairs of equations. I'll call the first equation equation 1, for second equation equation 2, third equation equation 3. So I'm going to pick two pairs. My first pair is going to be equation 1 and equation 2. So equation 1 is x minus 2y plus z equals 6. Equation 2 is x plus 4y minus z equals 10. And then I'll pick equation 2. Or excuse me, then I'll pick my second pair. Now, it doesn't matter which two pairs you pick. There's a lot of two pairs, but I'll just, for this case, pick equation number 2 and equation number 3. So equation number 3 is 2x minus 6y plus 2z equals 6. And we've already looked at equation number 2, which is 1x plus 4y minus z equals 10. So with these two pairs, I have to eliminate the same variable. I'm going to eliminate the variable z in both equations. I should say in both systems. Now, in this first half, you'll notice that to eliminate the z's, all I have to do is add the equations together. It's already set up like an elimination method where I can add the two equations together and eliminate a variable. That's because the variable z has opposite coefficients. So let's add the two equations up. Let me write that. Add equations together. So I'm going to get 2x plus 2y. My z's will cancel out, and I will have equals 16. Let's also eliminate z from my other pair of equations. Now, these two equations do not have opposite coefficients on the z's. So, I have to do this a little bit. Remember the elimination method. What I'm going to do is I'm going to take the 2 that's in front of this z, and I'm going to put it in front of my other equation. I'll take the -1 that's in front of this z and put it in front of this equation. Change the sign on one of them, and then multiply through. When I multiply through, I get the equation 2x plus 8y minus 2z equals 20. And 2x minus 6y plus 2z is equal to 6. Again, for a refresher on the elimination method and how I'm doing that, you can look up my elimination method videos. Now we're at a point where we can add the equations together. And when I add the equations together, I get 4x plus 2y is equal to 26. So now notice what I have. I started with two pairs of equations. I eliminated z on one of the pairs, and then I eliminated z on the other pair. And now I have two equations, both of which involve x and y. So that leads me to a system with two equations and two variables. My two equations are 2x plus 2y equals 16 and 4x plus 2y equals 26. We can eliminate a variable here if we want, in the same way, I take the 2 that's in front of the y in equation 2 here, I put it in front of equation 1. I take the 2 that's in front of the y on the other equation, I put it in front of equation 2. And then I change one of the signs from a positive to a negative. Multiply through. You end up with negative 4x minus 4y equals negative 32. And 8x plus 4y is equal to 52. Now, this is not the only way you could have eliminated. You could have used 1 and negative 1. If some of you are used to that, go ahead and do that. Now I add these equations together. When I add the equations together, I get 4x. My y's cancel out, equaling 20. Dividing both sides by 4 gives me an x of 5. Now I know I have x's of 5 now, so my x value I know has to be 5. To get the other values, I go back up. I can either use this equation or this equation. It doesn't matter which. I think I will use 2x plus 2y equals 16. And I'll replace the x with the number 5. And then solve that equation for y. Subtracting 10 from both sides gives me 2y is equal to 6. Dividing both sides by 2 gives me a y value of 3. Now I know that the x value is 5, the y value is 3, and so I want to find the z value. I use any of these first 3 equations to find my z value. I'll use equation 1, which says x minus 2y plus z equals 6. Now that I know x is 5, I replace the x with a 5. I know that y is 3. I replace the y with a 3. And this gives me an equation I can solve for z. 5 minus 2 times 3 gives me a negative 1 plus z equals 6. Adding 1 to both sides gives me a z equaling 7. So now I have my solution. My solution happens when x is equal to 5, when y is equal to 3, and when z is equal to 7. I can check that solution by plugging it in to all 3 equations and seeing that I get a true statement in all 3 equations. In this case, you would. I won't spend the time doing that in this video, but in this case, you would get a true statement in all 3 equations. And just to note, if you're trying to do like we have before, write your solution down as an ordered pair. We can't write it down as an ordered pair because obviously there are 3 numbers, but we could write it down as an ordered triple. And if you do that, usually the X comes first, the Y comes second, and the Z comes third. So that's the basics of how we solve a system with 3 equations and 3 variables. Let's try to do another example. In front of you, you see example 2, which says 3x minus 5y plus 2z equals 16. X plus 7y minus 3z equals 20. And 4x minus y plus 5z equals 12. We're going to try to find a solution to the system of these 3 equations. This is going to be very similar to our last example. So if you wanted to try it on your own and then see the final, the solution for this system at the end, that's perfectly fine. So let's take pairs of equations. It doesn't matter which pair you take, but we need 2 pairs. So I'll take equation 1 and 2. That'll be 1 pair. And then I'll take equation, let's do 2 and 3 again. Again, it doesn't always have to be these. In fact, let me just switch it up just so that we have a different pair of equations. I'll take equation 1 and equation 3. Oops. So here are my 2 pairs of equations. Let's decide to eliminate a variable. It doesn't matter which one. I know in the last example we eliminated the z's. So let's eliminate a different variable this time. Let's eliminate the y's first. If I'm dealing with equations 1 and 2, what I need to do is take the coefficient of y, put it in front of the opposite equation. So the coefficient of y in equation 2, put that in front of equation 1. The coefficient of y from equation 1, put that in front of equation 2. And remember, we changed the sign on one of them. So that -5 is going to change into a +5. Multiplying through gives me 21x minus 35y plus 14z is equal to, oh, I got to pull out my calculator to do this in my head. So 70 plus 42, 112. Making sure on my calculator that that is 112. All right. The other equation becomes 5x plus 35y minus 15z is equal to 100. Add these together. When we add these 2 together, we're going to get 26x minus 1z is equal to 212. Now that's one equation, or excuse me, that's one pair gave us that equation. My other pair is going to give us another equation. So take the other pair, equations 1 and 3, and we'll eliminate the y's on these. Again, you have to eliminate the same variable on both. So we take equation 1 and equation 3. In front of equation 1, we put a -1 because that's the coefficient of y in equation 3. And in front of equation 3, we put in front of that a -5. I have to change the sign on one of them. So I either change the -1 to a +1 or the -5 to a +5. Multiplying by +1 is really nice, so I'll do that. When I multiply through, I end up with 3x minus 5y plus 2z is equal to 16. And -20x plus 5y minus 25z is equal to -60. Now we add these together. And you end up, whoops, with -17x plus 0y minus 23z is equal to -44. So we have two equations that have variables only in x and z. We'll call these my xz equations just for sake of ease. So here's my xz equations. My first xz equation, 26 minus z equals 212. My second xz equation, -17x minus 23z equals -44. Now let's eliminate a variable. I'll eliminate the z's. So put -23 in front of my first xz equation. Put -1 in front of my second xz equation. And then change the sign on one of them. I will change the -1 to a +1. Multiply through. -23 times 26 is -598. Z times -23 is a plus 23z. -23 times 212 is -4876. When I multiply 1 through, I end up with -17x minus 23z equals -44. Add those two together. Let me write that down. -598 minus 17 becomes a -615x The z's are canceled out. And I end up with negative 4920 on the right-hand side. Dividing both sides by negative 615 gives me an x value, which is 8. So obviously we dealt with some ugly looking numbers here, but we ended up with an x value of 8. And now I can go back to one of these xz equations. I think I'll use the first xz equation and plug in 8 for that x value. Solving 26 times 8 is 208. So we end up with 208 minus z is equal to 212. Subtracting 208 from both sides gives you negative z is equal to 4, which means when you divide by negative 1, the coefficient of z, you get z of negative 4. Now I have the x value, I have the z value, so I go back up to one of my original x, y, z equations. I'll use the first x, y, z equation. Now that we know x is 8 and z is negative 4, we can solve when you take 3 times 8, you get a 24. When you take 2 times negative 4, you get a negative 8. 24 minus 8 is 16. So it ends up as negative 5y plus 16 is equal to 16. That 16 comes from 24 minus 8. Subtracting 16 from both sides gives you a negative 5y equaling 0. Dividing both sides by negative 5 gives you a y, which is equal to 0. So my solution should be x is 8, y is 0, z is negative 4. X is 8, y is 0, z is negative 4. And it's okay that one of the numbers comes out to be a negative. It's okay that one of the numbers comes out to be a 0. It's okay that one of the numbers comes out to be a positive. That's perfectly fine. If you wanted to do it as an ordered triplet, 8, comma 0, comma negative 4. Remember, we do alphabetical. When we're ordering our ordered pairs, or in this case, ordered triplets. So that's how it's done. Again, just as a refresher, you start with 3 equations, 3 variables. You pick 2 pairs, eliminate the same variable in each pair. In this case, I eliminated the y. If you do that, you'll end up with 2 equations and 2 variables. And in those 2 equations and 2 variables, that's a system of linear equations that we already know how to solve. So that 2 variable, 2 equations, we can solve using our normal methods, whether that's elimination or substitution is fine. And then we end up with 2 numerical values for the 2 variables. plug it in, and get the last numerical value for the last variable. Let's do another example. Now, this example has missing variables in some of our equations. I say missing, we can also think of the coefficient being 0. So our system of 3 linear equations with 3 variables has 3 equations. The first equation is x plus 3y equals 2. The second equation is 2x minus 4z equals 0. And the third equation is x plus y equals negative 3z equals 6. I misspoke on that third equation. X plus y minus 3z equals negative 6. So let's solve these. So we want to solve this system with 3 equations and 3 variables. And what I'm going to do is the same process as we did before. I'm going to pick 2 equations with 2 variables. So let me restate that. I'm going to pick 2 equations and I'll eliminate a variable. I'm going to pick equations 1 and 2 to be one pair of equations. And in my next pair of equations, again, it doesn't matter. I think I will pick, let's do equations 2 and 3. I think this will be good. Now, we have to decide which variable to eliminate. There's a number of ways you can look at this. Let's say we wanted to eliminate the variable z. So let's eliminate z. And we'll do that in both. In equations 1 and 2, when we set this up, you could think of this first equation being x plus 3y plus 0z's equals 2. In the second equation, this is 2x minus 4z equals 0. Now, the key part here is that when I do the trick of elimination, where I take the coefficient of one of my z's and I place it out in front of the other equation, I'm going to necessarily put a 0 in front of that second equation. That's already going to get rid of that second equation. I'm going to end up with 0 equals 0. It's not going to play a factor. And in this first equation, I just multiplied that equation by a negative 4 everywhere. So what I can do, if I want to eliminate z, I can just, instead of doing the elimination method, like I'm doing here, I can actually just ignore equation 2 because in equation 1, the z is already gone. So instead of trying to do this using elimination, I am going to cancel that out. And I'm just going to simply ignore equation 2 because the z is already gone in equation number 1. And I'm going to just reuse equation number 1. X plus 3y equals 2. That's an equation with 2 variables, x and y, and z has been eliminated. Now, in the other pair, there are z's in both equations, so I'm going to have to do the traditional method. Of writing -3 in front of the first equation, writing -4 in front of the second equation, changing the sign on one of those. I'll change the -4 to a +4, and then multiplying, giving me -6x. There's no y's. If you want to put +0y just as a spaceholder, you can. Minus 12z equals 0. And then 4x plus 4y. Oh, my apologies. On that first equation, that should have been a plus 12z. On the second one I get when I multiply through, I end up with 4x plus 4y minus 12z is equal to -24. Again, apologize for that mistake. We add equations together. And when we add the equations together, we end up with -2x plus 4y. The z's are eliminated, and you get equal to -24. So the whole thing here is that when you pick two equations, when you pick a pair of equations, and one of them already has the variable you want to eliminate eliminated, you can just ignore the other equation. So just simply use x plus 3y equals 2 if I wanted to eliminate the z in this first pair. Now I have two equations, two variables, x plus 3y equals 2, and -2x plus 4y equals -24. I do my standard technique of eliminating a variable. I think I will eliminate the x in this case. So I'll take my pair of equations. I'll write a -2 in front of the first xy pair. I will write a 1 in front of the second xy equation. Change one of the signs. It'll be easier to change the -2 to a +2. 2x plus 6y equals 4. And -2x plus 4y is equal to -24. Adding those equations together gives 10y equals -20. Dividing both sides by 10 gives a y value of 2. Once I have the y value, I grab one of my xy equations, doesn't matter which one, and plug in the y value of -2. Got to be careful, I missed a couple of negatives here. So y value of -2. Once you do that, you would add 6 to both sides. Now I have an x value of 8, a y value of -2. I go back to my x, y, z equations, and I want to solve for z. Obviously, I can't use this first equation. It doesn't have a z in it. But you could either use the second equation or the third equation. I'll use the second equation because that has fewer terms. Replace the x in that equation with the number 8. 16 minus 4z equals 0. Subtract 16 from both sides. -4z equals -16. Then divide both sides by -4. That gives you a z of +4. So there's my solution. X is 8, y is -2, z is 4. So x is 8, y is -2, z is 4. Okay. Now, because I made a couple of mistakes, I feel like I should probably check my answer. If you want to check your answer, plug in those values into each of these 3 equations. So in this first equation, you'd plug in an 8 for x and a -2 for y, and see that you get a true statement. That checks out. 8 plus 3 times -2 equals 2. Yep, that works. So that's good. In the second equation, we'd plug in an 8 for x and a 4 for z. 2 times 8 is 16 minus 4 times 4. So 16 minus 16 gives you 0. Yep, that's good. So it works in 2 equations. And then in the last equation, an 8 gets plugged in for x, a -2 gets plugged in for y, and a 4 gets plugged in for z. If I take 8 plus -2 minus 3 times 4, I do in fact get a -6. So that's also good. So I've checked my answers and my solution does work, which is good because I had mistakenly put a couple of negatives down. So that's my solution. X is 8, y is -2, z is -4. Let's take a look at this last example. This last example has a system of 3 equations with 3 variables. We're trying to find the solution to the system. One equation is set up as z is equal to 3x minus 2y plus 14. The other equations are x minus 4y minus z equals 16, and the equation x plus y minus 3z equals negative 27. There are a number of options you can utilize to solve this. If you really like the elimination method, you can rewrite this first equation so that the x's, the y's, and the z's are all on the left-hand side and they all line up. But since we've done that in the first 3 examples, I'm going to use a slightly different technique in this last example. Here's what I'm going to do. I'm going to pick 2 pairs of equations. And my first pair will be equation 1 and equation 2. My second pair will be equation 1 and equation 3. It's always a trick to get everything lined up in these columns. Now, once again, you could use the same method we did before just by moving the x's and y's to the left-hand side of the equation in equation number 1. But we're going to eliminate z in both equations. In this case, by substitution. Since we have one equation equaling having z equaling 3x minus 2y plus 14, what I can simply do is take my other equation, x minus 4y minus z equals 16, and substitute in the expression 3x minus 2y plus 14 in for z. I'll clean that up a little bit. When you distribute your negative sign, you get negative 3x plus 2y minus 14 equals 16. Then I'll combine like terms and then also add 14 to both sides. When I combine like terms, I end up with negative 2x minus 2y equals 14 plus 16 gives me 30. And then I'll do the same on the other pair. I'll take x plus y minus 3z equals negative 27. And I will replace the z in that equation with the expression 3x minus 2y plus 14. Get a little bit messy there. It's a long equation. So x plus y minus 9x plus 6y minus 3 times 14 is 42 equals negative 27. Combining like terms and adding 42 to both sides gives you negative 8x plus 7y equals 15. So I can use substitution to eliminate the variable z as well. So if you don't like the elimination method, substitution method is available to you. Now in both cases, in both cases, I've eliminated the same variable. Okay, you still have to eliminate the same variable in both cases. So now I have a pair of two equations and two variables. We've been solving this two equation, two variable pair using elimination. But I think what I'll do this time is solve by graphing. Since we have two equations and two variables, that lends itself to being able to be solved by graphing. So let's do that. For that, we have to turn to Desmos. Let's type in both equations, negative 2x minus 2y equals 30. I should say you turn to Desmos or any other graph system of graphing that you want. If you wanted to graph by hand, you could graph by hand. If you wanted to use a TI-83 calculator, a TI-84 calculator, that would be fine as well. I'm just using Desmos because that's fast and it has a nice interface where I can grab the graph and move it around. So you can see that these two lines cross at the point -8, -7. Therefore, the solution to this system of two equations and two variables happens when x is equal to -8 and y is equal to -7. So we can use that as our solution to the two. So we solved by graphing. We got that x is equal to -8 and y is equal to -7. Now we're not done yet. Remember, this is the solution to the xy two equations, two variable system. Now that I have that, I need to figure out what the z value is as well. Since I have this equation already solved for z, I might as well utilize it. Plug in a -8 for your x and a -7 for your y. On the right-hand side, you're going to get, a number. When I take 3 times -8 minus 2 times -7 plus 14, I end up with a +4. So it looks like my solution happens when x is equal to -8, when y is equal to -7, and when z is equal to a +4. If I do have questions about that, if I think I'm not 100% sure that I solved that correctly, then you can always check by plugging it in to all three equations and seeing that you get a true statement for each equation. In this case, you will. In this case, we do have the right solution here. So those are 4 examples of how to solve a system which has 3 variables and 3 equations. We always want to pick 2 pairs of equations out of our original 3. We want to eliminate the same variable in each pair of equations. You can use elimination or substitution to do that. Once we've eliminated the same variable, that gives us 2 equations and 2 variables. We solve the system of 2 equations and 2 variables using one of the methods we've used before. And then lastly, once we've done that, once we have the 2 equation and 2 variables system solved, there's one variable that we eliminated originally that we need to solve for. So we solve for that last variable. So that's how to solve a system with 3 variables and 3 equations.